In this lecture, we begin our discussion on the quantum mechanical theory of the atom. This is basically the theory that uses quantum mechanics to describe the structure of the atom. So let's begin by recalling an earlier model of the atom as described by Niels Bohr that became known as the Bohr model. So according to the Bohr model, if we take the simplest atom, for example, the ground state hydrogen atom, the proton and the neutron within that atom is found at the center of that atom in a localized region known as the nucleus. And according to the Bohr model, which treats the electron as a particle, the electron orbits the nucleus on a well-defined circular pathway that corresponds to a quantized amount, a discrete amount of energy, as shown in the following diagram. Now, according to quantum mechanics, electrons do not actually reside on defined circular orbits as described by the Bohr model, and that's because of the wave-particle duality of nature. So, according to quantum mechanics, electrons do not only act as particles, but they can also act as waves. In fact, in quantum mechanics, we use a wave equation known as the wave function given by the Greek symbol psi to actually describe the motion and behavior and location of our electron. Now, what exactly is the difference between a particle and a wave? So a particle is basically an object that is found within a localized region in space. However, a wave extends over a very large region of space. A wave is not actually localized. Now, since waves are not localized and electrons can behave as waves, we can think of the electrons as being spread out over a large region of space around that nucleus as if those electrons were clouds. So these clouds that electron form is known as the electron cloud. Now, the size and the three-dimensional shape of these electron clouds can be readily obtained by using Schrödinger's equation. For example, as we'll see in a future lecture, if we solve Schrödinger's equation for the ground state of the hydrogen atom, we get the following equation. So the wave function that depends on the position x is equal to 1 divided by the square root of pi multiplied by x naught to the power of 3, and this ratio is multiplied by e to the power of negative x divided by x naught, where x naught is simply the Bohr radius of our atom. So we're going to examine this equation in much more detail in a future lecture. So basically, because of the wave-particle duality of nature and because the Bohr model describes the electron only as a particle, the Bohr model is not a correct description of the structure of the atom. And that's exactly why we use a new theory, a new model known as the quantum mechanical model, which uses quantum mechanics to describe the structure and behavior of our atom. So, let's move on to the following diagram. Now, if we take this wave function and we take the square of the absolute value of the wave function, that will give us something known as the density of that electron cloud. And the density is described by the following diagram. So basically, we see that for the ground state of the hydrogen atom, the electron cloud takes the shape of a symmetrical three-dimensional spherical shape. Now, of course, for more complicated atoms and electrons, we have different shapes. But for the hydrogen ground state, the shape is in fact a spherical shape. So notice, as we move farther away from the nucleus of our atom, from the center of the atom, the density becomes less dense. Now, what exactly is the meaning? How exactly can we interpret this diagram? So from the diagram, we see that the electron cloud gets less dense as we move farther away from the center of that atom. Now, if we imagine that the electron is in fact a particle, then the cloud density represents the probability density or the probability distribution of our electron as if it was a particle. So that is, this cloud density represents the probability of finding the electron at some position away from the center of our atom. So the more dense a given region is, the more likely that the electron is found within that specific region. The less dense our region is, the farther away our two blue dots are, the less likely our electron is found within that specific region. So we see from this diagram that our electron is most likely found within the following spherical shape. Now, what exactly are the implications of the quantum mechanical theory of our atom? Now, we see that since the electron actually occupies a large region of space because we treat our electron as if it was a wave and not a particle, and because there is always some probability of finding the electron at some finite position x, as per this equation, we see that this idea suggests that atoms are not mostly empty space, because at any given location around the center of our nucleus, around the center of the atom, there is some quantity, some amount of probability that the electron is found within that specific region.